Welcome back. So in episode 3 of this explainer series, we saw something literally mind-blowing. We looked at how using the right index can take a sluggish 10-second query and instantly turn it into a lightning-fast 1 millisecond query. I mean, that is a 10,000x speedup. But here's the crazy part, and it's something I see all the time. Most developers unfortunately only know about one type of index. They just blindly rely on the default B tree. But what happens when that default just isn't enough? Well, using the wrong index doesn't just fail to speed things up, it can actually actively slow your entire database down. The truth is, every major database ships with at least 4 or 5 completely different index types, and every single one is purpose-built for a specific kind of query. So today, we're breaking them all down.
All right, let's dive right into this. What you're looking at here is a blank blueprint. This is our master index decision table. And I promise you, by the end of this explainer, you are going to absolutely master this exact table. You'll know exactly which index to pull out for literally any situation, which is going to transform you into that go-to developer who knows exactly how to optimize even the most stubborn, painfully slow queries.
Let's start with a really quick recap from episode 1. The B-tree index. Now this is your default in PostgreSQL, MySQL, SQL Server, SQLite, you name it. Think of the B-tree as your trusty Swiss Army knife. It is a balanced tree structure that stores your entries in a beautifully sorted order. Because it's sorted, it's incredibly efficient for your standard equality lookups, like say finding user ID 42. And it's great for range queries too, like finding users between the ages of 20 and 30. But look, as versatile as a Swiss Army knife is, you wouldn't use it to chop down a giant redwood, right? It dangerously fails at some very specific, very common modern tasks.
Let's look at exactly where the B tree falls short, because there are 4 major blind spots. First, pure equality lookups on high cardinality columns. Believe it or not, there's actually a much faster way to do this than a B tree. Second is full-text search. If you're searching for a word with a leading wildcard, like looking for a specific keyword buried anywhere inside a long product description, a B tree is totally useless, because it relies on reading from left to right. Third, it completely fails at looking inside arrays or JSON structures. It just sees the whole block of data as one big blob. And fourth, geospatial queries. If you need to find a location within a 5-mile radius, well, B-trees only sort in one single dimension, so they absolutely cannot help you with multidimensional map data. These 4 limitations create a massive knowledge gap for most developers, and that is exactly what we are going to fill today.
Real quick before we solve those, if this is the kind of content you want more of, subscribing takes 1 second and it genuinely helps the channel grow.
Okay, so how do we solve that first limitation, pure equality lookups, where we need absolute maximum speed? Enter the hash index. Instead of traversing down a layered tree structure like a B tree, a hash index takes your indexed value, calculates a mathematical hash of it, and maps that directly to the exact row location on disk. Because it uses a hash table under the hood, your lookup speed is big O of 1, constant time. That means it literally doesn't matter if your table has 1,000 rows or 1,000,000,000 rows, it takes the exact same microsecond to find your data.
Think of a hash index exactly like a coat check at a nice restaurant. You hand the attendant your coat, that's your data value, and they hand you back a ticket, which is the hash. Later, when you want to leave, you hand them that exact ticket, and boom, you get your coat back instantly. It is absolutely perfect for instant, exact retrieval. But imagine walking up to that same coat check and saying, "Hey, can you give me all the red coats?" Or, "Can I have all the coats checked in between 8 p.m. and 9 p.m.? The system completely breaks down. It's useless. Hashing destroys the original sort order entirely. So you want to use this for things like session stores or exact user ID lookups, but absolutely never for range queries.
All right, let's tackle our next big limitation, searching inside values. Think full-text search or digging through arrays. For this, we are going to pull out the GIN index, which stands for Generalized Inverted Index. Now, if you are using MySQL, your equivalent here is the full-text index. Instead of indexing the whole column value as one single unbreakable chunk, a GIN index actually decomposes the value. For a massive text column, it separates and indexes every single word individually. For an array, it indexes every individual element.
And this brilliantly illustrates why GIN is an absolute game changer. Think of it like the index at the very back of a massive college textbook. Instead of pointing to the whole book, it lists every individual keyword alphabetically and tells you the exact page numbers where that specific word appears. If you want to find the word database, you aren't going to sit there and read the entire book starting from page 1, right? You look at the back, find database, and skip instantly to page 412.
This entirely eliminates those massive, sluggish, full table scans when you're dealing with full-text search, complex arrays, or rich JSONB data.
Now, what about geospatial data? For that, we use the GIST index, or generalized search tree. Again, for my MySQL users out there, you'd be looking for spatial indexes to do this job. Unlike a standard B tree that strictly relies on simple one-dimensional less than or greater than alphabetical sorting, GIST is a highly flexible framework. It is designed specifically to support multi-dimensional data and weird, non-standard data types.
To wrap your head around it, a GIST index acts much more like a visual topic map. Imagine sorting a massive library of books strictly alphabetically by title. That's our B tree. Completely useless if you want to find books where the themes naturally overlap, right? Like finding books about both machine learning and statistics. GIST understands spatial proximity and overlaps. So if you need to find all the coffee shops within a 2-kilometer radius of a user's phone, or you need to find hotel bookings with overlapping calendar dates, GIST is your go-to. It actually maps the relationships and boundaries between data points, rather than just forcing them into a straight, linear line.
Okay, let's pivot for a second. We've talked about the structural types of indexes, but let's talk about strategic indexing, because this is where you go from being a good developer to optimizing your database like an absolute pro. Let me introduce you to the partial index. A partial index drastically reduces its storage footprint and its maintenance overhead by only including rows that match a specific where condition. You are literally telling the database to index only the exact subset of rows you actually care about and plan to query.
Think about it like a VIP guest list. If you're running security at a massive event with 10,000 attendees, but only 50 of those people are VIPs getting special backstage access, you wouldn't hand your door staff a massive 10-pound directory of all 10,000 people. No way. You give them a specialized one-page list of just those 50 VIPs. It is infinitely faster to check. Translating that to your database, if your application constantly queries for e-commerce orders where the status is strictly pending and only 2% of your total historical orders are actually pending, well, a partial index on just that 2% is going to be tiny, lightning fast to update, and incredibly efficient to search. Next up, let's look at the composite index. This is an index that spans multiple columns at the exact same time. But I really have to warn you here, this comes with a major catch. Honestly, getting this wrong is the single most common indexing mistake I see, and it trips up even senior developers constantly. The database can only utilize this index based on a very strict mathematical rule regarding the column order.
Think of a composite index exactly like an old-school printed phone directory. The phone book is sorted first by last name and then by first name. So if you're looking for Smith John, you flip to the Smiths, then you easily find John. Instant. If you just want to find all the Smiths, also instant. But what if you only know the person's first name is John? Well, suddenly, that giant phone directory is entirely useless to you. Because it's sorted by last name first, you would literally have to read every single page of the book to find all the Johns.
And this brings us directly to the leftmost prefix rule. Column order is absolutely everything here. The database can only use the index starting from the leftmost column, and it cannot skip columns, period. If your composite index is built on last name and then first name, a query filtering only on first name is going to ignore the index completely and trigger a slow, painful, full table scan. So, write this down. The golden rule you must remember. Always place your most selective column, the one that filters out the most rows, first in your index.
Finally, we reach the holy grail of optimization, the covering index. A covering index goes above and beyond normal filtering by actually including all the columns you need to return in your select statement right inside the index itself. When your index physically holds everything the query is asking for, the database completely bypasses the main table. This is the exact secret mechanism that enables those lightning-fast index-only scans we discussed back in episode 3.
To really visualize this, imagine looking at a restaurant menu. A covering index is like a well-designed menu that lists both the name of the dish and its price. If you just want to know how much the burger costs, you simply look at the menu in your hand. You don't need to get up, walk into the kitchen, or track down a waiter to ask for more information. The index covers your entire request. By explicitly adding your select columns directly into the index, you completely eliminate those expensive trips to the main table.
Okay, we have covered a ton of ground today. Let's put all this brand new knowledge to the test with 3 quick, real-world scenarios. Scenario 1. You're building an e-commerce app, and you need to search for products that have the word wireless buried anywhere inside their massive text descriptions. Which index are you reaching for? Take a second.
Got it? The answer is the GIN index, or full text if you're on MySQL. Because we need to search inside the text values instantly, decomposing that massive text block into individual searchable words, a standard B tree wouldn't stand a chance without wildcard search. But GIN handles it perfectly.
Let's try scenario 2. You're working on the back end for a ride-sharing app, a user opens the app, and you need to immediately query the database to find all active drivers within a 5-mile radius of the user's exact GPS coordinates. Which index is going to handle this complex multi-dimensional math?
You guessed it, the GIST index, or spatial index. It is built specifically to map out multidimensional proximity, allowing your database to instantly calculate that 5-mile radius overlap without scanning the whole massive driver table.
All right, final one, scenario 3. You are optimizing a social network's backend authentication. You need to execute a direct, exact lookup for a user's profile using their unique exact user ID. No ranges, no wildcards, just pure, precise equality. What is the absolute fastest tool for the job?
The hash index. Because you're looking for a pure equality match, the hash index takes that ID, hashes it, and maps directly to the row location on disk. It completely bypasses any tree traversal, delivering blazing fast, constant time 01 speed. Nothing beats it for this specific job.
And there it is. Take a look at the fully populated index decision table we promised you at the start. We just went from knowing only the basic default B tree to possessing a highly specialized expert toolkit for pure equality, full-text search, geospatial mapping, and advanced multi-column strategies. Seriously, save this decision table. It is your new superpower for optimizing any database. But look, understanding how to fetch data incredibly fast on one single server is really only half the battle. What actually happens to all these specialized, beautifully crafted indexes when you need to copy your data across multiple servers around the entire world? How do these complex index types handle database replication? Well, that is a massive architectural challenge, and we are going to tackle it head-on in episode 5 of this explainer series. Thanks so much for joining me today, and I'll see you in the next one.